You know that feeling, right? When your brand new phone doesn't feel that much faster than your old one? Well, it's not just a feeling. The truth is, computing has kind of hit a wall. So today, we're going to dive into a fundamental breakthrough that could change absolutely everything. A chip that doesn't just calculate, it actually thinks.
Okay, so let's get right into it. Have you noticed how your new laptop or phone doesn't seem to have that mind-blowing speed jump over the one you had a couple of years ago? It feels like those days of massive performance leaps are, well, they're slowing down. So what's the deal? What's the holdup?
You know, the funny thing is, this problem isn't new at all. In fact, it's been baked into the very design of every digital computer for the last 75 years. It's this core flaw that we've managed to just outrun for decades by making everything smaller and faster. But now, we've pretty much hit a physical wall.
To really get this, we need to talk about something called computing's great traffic jam. And it's not just a clever name. It really is the core bottleneck that's holding everything back, from our phones all the way up to the most powerful AI on the planet.
And this right here, this is the source of that traffic jam. It's called the von Neumann architecture, and for 75 years it's been the blueprint. It keeps the processor, the logic, physically separate from the memory. Now imagine a chef whose ingredients are all stored in a completely different building. Every single thing they need to cook, they have to run outside, go get it, and bring it back. It's a huge waste of time and energy. For simple stuff, it's just inefficient. But for something as complex as AI, well, it's a crippling bottleneck.
So, how do you fix a 75-year-old problem? Well, it turns out we can look to a much, much older and way more efficient computer for some inspiration: the human brain. And this is where this whole idea of bio-inspired computing comes into play. So meet the hero of our story, the memristor. The name itself is a mashup of memory and resistor. And the magic of this little component is that it has a dual personality. It can store information, just like memory, and it can process that information in the exact same spot. It's a lot like a synapse in our brain. Remember our chef running back and forth? The memristor basically puts all the ingredients right next to the stove. The commute is totally gone.
So we've got these incredible new building blocks, right? These artificial synapses. Now let's take a look at how they're actually used to build a completely new kind of computer from the ground up.
Step 1 is the most direct fix: in-memory computing. By using memristors, we can do the actual calculations right where the data is being stored. And just like that, poof! The traffic jam is gone. There's no more of that wasteful shuttling of data back and forth. This one change alone makes computing radically more efficient, both in speed and in energy.
Now, let's move to step 2, AI acceleration. You see, modern AI depends on this one super heavy-duty type of calculation over and over again. It's called vector matrix multiplication. It's really the workhorse of all deep learning. When you arrange these memory stores into a dense grid, they can perform these massive, complex calculations all at once in a single step, just using the laws of physics. It's like the architecture was tailor-made for what AI needs to do.
And step 3 is where things get truly, well, brain-like. Instead of processing a continuous stream of data, these networks can communicate using these little, distinct spikes of electricity, just like our neurons do. This is the whole idea behind what are called spiking neural networks, or SNNs. The motto here is computing with time, not just in time. It's an incredibly efficient way to process information, and it takes us one giant step closer to mimicking the brain's amazing efficiency.
Okay, so that's all the tiny, microscopic technology. But what does it mean for the real world? Let's zoom out a bit and look at what this means for the dawn of smarter robots.
I mean, this is really the key question, isn't it? How does a chip that thinks more like a brain actually translate into a machine that can act intelligently out there in the physical world?
Well, it gives them the power of perception. It doesn't matter if it's a big industrial arm on an assembly line or a four-legged explorer navigating a disaster zone. These neuromorphic chips give them the onboard brain power to make sense of their environment in real time without needing a constant connection back to some massive data center in the cloud. And this kind of enhanced perception, it just unlocks a whole new level of what these robots can do. We're talking about automating repetitive jobs with way more precision, working in hazardous environments to keep humans safe, or even assisting in complex surgeries with superhuman stability. They can deliver goods, medicine, and maybe most importantly, perform search and rescue in places that are just too dangerous for people.
But for a robot to be truly autonomous, to be truly on its own, it needs to solve this classic chicken and egg problem called SLAM. That stands for simultaneous localization and mapping. I mean, think about it. To build a map, you need to know where you are. But to know where you are, you kind of need a map. So how do you solve both at once?
Let's walk through how it works. So imagine our robot, a little triangle, enters a room it's never seen before. It can see a few distinct features, and it treats them as landmarks. Those are the stars. At this point, though, its own position is pretty uncertain.
Next up, it uses its sensors, things like cameras or LiDAR, to measure its relationship to those landmarks. It sends out signals and gets a sense of the distance and the angle to each one. It's basically just gathering a ton of raw data about its surroundings.
And here's the final crucial step. The robot takes all that sensory data and uses it to update its belief about its own position. See that shrinking zone of uncertainty? With every new measurement it takes, its location becomes more certain, and its map of the room becomes more accurate. It's solving both problems at the exact same time. It's pretty cool.
Now, this all sounds revolutionary and, well, it is. But like with any truly groundbreaking technology, it's really important to have a reality check. We're not quite there yet. There are still some pretty significant hurdles to overcome.
Right now, researchers are tackling 4 major challenges. First, there's programming variability. It's just hard to get these components to behave with perfect precision every single time. Then their response isn't always linear, which can really complicate the math. Third, the values they store can drift over time. Think of it like a memory that's slowly fading. Not great for a robot trying to remember a map. And finally, just building these into massive, reliable arrays is a huge engineering hurdle. Overcoming these is the key to taking this out of the lab and into our devices.
But if we overcome these challenges, and it's a big F, it brings us face to face with a question that goes way beyond just engineering. It really starts to get into philosophical territory. What exactly are we building here?
This quote from the researchers really just hits the nail on the head. The old way of doing things was to program logic onto a chip. This new way is fundamentally different. It's about understanding the physics of a material so deeply that you can use it to directly reproduce the dynamics of a biological process, like learning. We're not just simulating a brain anymore. We're building a system that processes information using some of the very same physical principles.
And that brings us to our final and maybe most profound question. As we create machines that can learn and perceive and navigate the world using brain-inspired hardware, are we simply building faster, more efficient tools, or are we on the verge of creating something more? A new form of intelligence, born not from silicon logic, but from the very physics of matter itself. What do you think?